The morning of October 14th, 1943, started with the kind of silence that settles over an airfield when men know what's coming. At Thorpe Abbotts in England, 291 B-17 flying fortresses sat on hardstands, their aluminum skins catching the pale autumn light. Ground crews moved between them with practiced efficiency, loading bombs, checking engines, filling fuel tanks. The target for the day was Schweinfurt, deep in the heart of Germany, 370 miles from the English coast. The ball-bearing factories there were keeping the German war machine running, and 8th Air Force had been ordered to destroy them. The mathematics were brutal, and everyone knew it. The P-47 Thunderbolts could escort the bombers for maybe 375 miles with drop tanks. Then they'd have to turn back, and the fortresses would be alone over Germany for hours, flying through flak and fighters with nothing but their own guns for protection. By sunset, 60 B-17 seconds were gone. 600 men, some shot down by German fighters that swarmed the formations the moment the escorts turned back. Some crippled by flak and forced to ditch in the North Sea. Some that simply ran out of fuel trying to limp home on damaged engines. The crews that made it back landed in the dark, some of their aircraft so shot up that ground crews counted over 200 holes in a single airplane. The debriefing rooms at bases across East Anglia filled with exhausted men who'd watched friends die and knew they'd have to go back up tomorrow. In the intelligence reports filed that night, one phrase appeared again and again: without fighter escort to target and back, losses are unsustainable. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. This wasn't new information. Everyone from General Ira Eaker commanding 8th Air Force down to the Broomer, newest replacement pilot, understood the problem. American doctrine called for daylight precision bombing. Hit the factories, the refineries, the infrastructure that kept Germany fighting. But daylight meant visibility, and visibility meant German fighters could find you. The Royal Air Force had tried daylight bombing in 1940 and 1941 and taken such catastrophic losses that they'd switched entirely to night operations. Bomber Command flew at night, dropped their loads on cities, and accepted that precision was impossible. The Americans insisted they could do better. The Norden bomb site, they argued, could hit a pickle barrel from 25,000 feet, and the B-17 flying fortress, with its heavy defensive armament and rugged construction, could fight its way to the target and back without fighter escort. Black Thursday proved that doctrine was built on optimism rather than reality. The B-17 could absorb tremendous punishment. That part was true. Crews told stories of fortresses coming home with entire sections of fuselage shot away, with engines dead, with control surfaces shredded. The airplane earned its reputation for bringing people home, but it couldn't do the impossible. It couldn't outrun fighters. It couldn't hide. And when German pilots developed tactics specifically designed to defeat bomber formations, when they started making head-on attacks that the B-17's defensive armament couldn't adequately counter, the losses mounted. The only solution was fighter escort, fighters that could stay with the bombers all the way to the target, fight off the German interceptors, and escort the fortresses home. But in October 1943, no Allied fighter had the range to do that. The P-47 Thunderbolt was a magnificent fighter, fast and heavily armed, but its combat radius topped out around 375 miles, even with drop tanks. The P-38 Lightning had better range but was still stretched thin escorting bombers to targets in western Germany. And the P-51 Mustang, which would eventually solve the escort problem with its combination of performance and range, was just beginning to arrive in theatre in small numbers. The bombers were on their own for the deepest penetration missions, and the losses were going to continue until something changed. What needed to change, more than tactics or aircraft design or defensive armament, was range. Not fighter range, though that mattered too, bomber range. Because every mission planner in England was working with the same cruel calculus. The farther the target, the more fuel required. The more fuel required, the fewer bombs you could carry, or the less fuel you could carry for defensive maneuvers and emergencies. The B-17E and early B-17F models carried 1,700 gallons of fuel in 6 wing tanks, 3 tanks in each wing, feeding the 4 Wright Cyclone engines. At cruise power, that gave them an operational range of about 2,000 miles total, which sounds adequate until you factor in the realities of combat operations. You didn't cruise at economical power settings over Germany. You flew tight formations at high altitude, engines working hard to maintain position. You took evasive action when flak came up, you maneuvered when fighters attacked, and sometimes you came home on 3 engines or even 2, burning fuel faster and losing altitude, praying you'd make it across the channel before the tanks went dry. Mission planners calculated that the effective combat radius, the distance a B-17 could fly to a target with a reasonable bomb load and still make it home with a safety margin, was about 320 miles. Targets beyond that were possible but risky. Targets significantly beyond that were essentially suicide missions unless weather conditions were perfect and German opposition was light, which it never was over important industrial targets. So, for the first year of operations in Europe, large parts of inside teams over Levelation, Germany remained untouchable. The planners would brief missions to targets in the Ruhr Valley, to targets in occupied France, to coastal targets that were barely across the German border. But Berlin, 460 miles from the English coast, might as well have been on the moon. The engineers at Boeing's Seattle plant understood this before the first B-17 even arrived in England. They'd been working on bomber designs since the mid-1930s, and they knew the fundamental truth of aviation. Everything is a trade-off. More armor means less speed. More guns mean less bomb capacity. More range means bigger fuel tanks, which means more weight, which means either less payload or structural modifications to handle the additional load. The B-17 had been designed in 1934 and 35 with specific parameters. It needed to carry a meaningful bomb load, defend itself with multiple gun positions, operate at high altitude to avoid flak, and have enough range to hit targets several hundred miles inland. Those requirements drove every design decision. By 1941, when the United States entered the war and B-17 production ramped up dramatically, Boeing engineers were already receiving feedback from the field. The British had operated a few early B-17Cs and reported that the aircraft needed more fuel capacity for European operations. Combat radius needed to increase. But how? You couldn't just bolt bigger fuel tanks onto an existing design. Aircraft engineering doesn't work that way. Every system is integrated, every component balanced against every other component. Adding fuel capacity meant adding weight. Adding weight meant either accepting reduced performance or strengthening the structure. Strengthening the structure meant more weight. And around the problem went, with each potential solution creating new complications. The Boeing engineering team, working out of Plant 2 on the south shore of Lake Washington, approached the problem methodically. They had the B-17E in production, with its revised tail design and additional defensive armament. The B-17F was on the drawing boards, incorporating hundreds of detail changes based on combat experience, but the range problem remained. Some engineers proposed external drop tanks, similar to what fighters were beginning to use. That would work for ferry flights, but was impractical for combat operations. Drop tanks hanging under the wings or fuselage created drag, reduced speed, made the aircraft less maneuverable. And if you had to drop them before reaching the target to fight off German interceptors, you'd just made your fuel situation worse, not better. Other engineers suggested increasing the capacity of the existing wing tanks, but the tanks were already sized to fit within the structural limitations of the wing. Making them bigger would require widening the wing or thickening it, either of which would require a complete redesign. That might be possible for a future aircraft, but it wouldn't help the B-17 seconds that were already flying combat missions or sitting on production lines. The solution needed to work with the existing airframe. It needed to be something that could be incorporated into production without massive retooling. And ideally, it needed to be something that could be retrofitted to aircraft already in service, though that turned out to be impractical for reasons that would become clear later. The breakthrough came from looking at the B-17's wing structure itself. The wing consisted of two main sections per side, an inboard wing panel that mounted to the fuselage and carried the engines and flaps, and an outboard wing panel that bolted to the inboard section and carried the ailerons. Where those two panels joined, there was substantial structural reinforcement. The joint was a load-bearing point, engineered to handle the stress of flight loads distributed across the entire wingspan. And within that structural framework, between the ribs and spars that gave the wing its strength, there was empty space, not much, but some. Space that was currently filled with nothing but air. What if that space could be filled with fuel? Not rigid metal tanks that would require extensive structural modifications, but flexible, collapsible cells made of rubber composition material. Self-sealing cells, using the same technology that had already been incorporated into the B-17's main fuel tanks to prevent catastrophic fuel loss when the aircraft took battle damage. If you could fit 9 individual cells into each wing, positioned carefully to avoid interfering with flight controls or structural elements, you could add significant fuel capacity without major redesign. The cells would conform to the available space. They'd drain by gravity, feeding fuel to the existing feeder tanks that supplied the engines. And because they were collapsible, when they emptied, they wouldn't add much weight or create unnecessary drag from empty tank volume. The concept was elegant in its simplicity, but the devil lived in the engineering details. How much fuel could actually fit in the available wing space? How would you route the fuel lines? How would you prevent the cells from shifting in flight and potentially damaging the wing structure or control systems? How would you control fuel flow from cells that had no pumps and relied entirely on gravity feed? And most critically, how would pilots manage a fuel system where they couldn't see how much fuel remained in the new tanks? The existing fuel gauges monitored the main wing tanks. The new cells would be invisible to the cockpit instrumentation. Fuel would drain from them into the feeder tanks, but the pilots would have no way of knowing when the cells were full, half empty, or completely drained. The engineering team worked through these problems one by one, in meetings that ran late into the night and filled blackboards with calculations about weight, distribution, fuel flow rates, and structural loads. They built mock-ups, tested materials, ran simulations of flight conditions. By early 1942, they had a workable design, 9 rubberized self-sealing cells per wing, 18 total, 5 cells in the outboard wing section, totaling 270 gallons capacity, 4 cells in the inboard wing section and at the junction point, another 270 gallons. The same arrangement mirrored on the opposite wing. Total additional capacity, 1,080 gallons. 1,080 gallons sounds like a lot of fuel, until you consider what a B-17 consumed. At normal cruise power, all 4 engines running efficiently, the aircraft burned approximately 200 gallons per hour. So 1,080 gallons translated to roughly 5.5 additional hours of flight time. But flight time isn't the same as range. You're not flying in a straight line. You're climbing to altitude, which burns extra fuel. You're maintaining formation, which requires constant throttle adjustments. You're potentially taking evasive action or fighting your way through opposition. The additional fuel wouldn't double the B-17's range, but it would extend combat radius by approximately 400 miles, from 320 miles to over 650 miles. That was the difference between barely reaching Western Germany and being able to hit targets anywhere in the Reich. The modified fuel system received an unofficial nickname that stuck immediately: Tokyo Tanks. The name was ironic, almost sardonic. Adding 1,080 gallons didn't give a B-17 anywhere near enough range to fly from any Allied base to Tokyo and back. The designation was aspirational, a way of saying these tanks add serious range, the kind of range you'd need for truly long-distance missions. It was also hyperbole, the engineering team's inside joke that captured both the ambition and the limitations of what they'd created, but the humour masked deadly serious intent. These tanks were going to change what the B-17 could do. Boeing began incorporating the Tokyo tank system into B-17F production in early 1942, but the rollout was gradual. Aircraft built by Boeing from Block 80 onward got the tanks as standard equipment. Aircraft built by Douglas at their Long Beach plant got them from Block 25 forward. Lockheed Vega's Burbank facility started installing them at Block 30. The staggered implementation reflected production realities. Each plant had to tool up for the modifications, train workers on the new installation procedures, establish quality control protocols. You couldn't just stop the production line and change everything overnight, not when the Army Air Force was demanding aircraft as fast as they could be built. The first B-17Fs, with factory-mounted Tokyo tanks, arrived in England in April 1943. The 94th and 95th bomb groups received them first, and the aircraft were immediately distinctive to anyone who knew where to look. From the outside, they appeared identical to earlier B-17Fs. But inside the wings, the rubberized cells nestled between structural ribs, plumbed into the fuel system with control valves that crew chiefs could access from the bomb bay. Ground crews had to be trained on the new system, pilots had to learn new fuel management procedures, and everyone had to understand the limitations. The cells couldn't be monitored directly. They drained by gravity, which meant fuel flow was slower than from the pumped main tanks, and they had to be manually activated using valves in the bomb bay or radio compartment, depending on the specific aircraft configuration. By June 1943, replacement B-17 seconds arriving in England came with Tokyo tanks as standard equipment. By July, virtually every new fortress reaching 8th Air Force had the extended range fuel system. The impact on mission planning was immediate and profound. Targets that had been marked too distant suddenly became viable. German industrial complexes in central Germany, cities and factories that had operated with relative impunity because Allied bombers couldn't reach them effectively, found themselves within range. The additional 400 miles of combat radius opened up new targeting options and changed the strategic calculation. German forces had to defend a much larger area. Resources that might have been concentrated near the coast or in the Ruhr Valley had to be dispersed deeper into Germany. The Tokyo tanks didn't eliminate the escort problem. B-17 seconds with extended range still needed fighter protection, and the fighters still had their own range limitations. But the tanks bought time. They bought options. They meant that when the P-51 Mustangs arrived in numbers in early 1944 with their own exceptional range, the combination of long-range bombers and long-range fighters could finally implement the strategic bombing campaign as originally conceived. Deep penetration raids to targets throughout Germany with continuous fighter escort became possible. The air war over Europe entered a new phase, one where nowhere in the Reich was safe from American daylight bombing. But in the fall of 1943, the full impact of the Tokyo tanks was still emerging. The system had bugs that needed to be worked out. Pilots were learning through experience how to manage fuel from cells they couldn't see. Ground crews were discovering that the rubberized cells, while effective, could develop leaks if not properly maintained. And in combat, the vapor buildup in partially drained cells presented an explosion hazard. The cells were specified as self-sealing, which they were, but only if the sealant had time to work. A 20mm cannon shell or a piece of flak hitting a cell that was half full of fuel and half full of fumes could ignite the entire Lemeth tank, turning the wing into a fireball. These were the kinds of problems you couldn't identify until the system operated under real combat conditions. The engineering team back in Seattle heard about them through channels, combat reports that filtered back through 8th Air Force headquarters, through Material Command, through technical representatives who visited the bomber bases in England, and they worked on solutions, better sealant compounds, modified cell construction, improved procedures for fuel management. The Tokyo tank system, like every other aspect of the B-17, evolved through an iterative process of deployment, combat testing, failure analysis, and refinement. This was engineering under pressure, where getting it right meant crews came home, and getting it wrong meant they didn't. The operational records tell the story in numbers that don't capture the human reality, but document the impact nonetheless. Between April and December 1943, 8th Air Force flew 127 missions that exceeded the B-17's original operational radius. Missions to targets like Regensburg, Schweinfurt, Augsburg, Stuttgart, cities and industrial centers deep in southern Germany that had been functionally unreachable 6 months earlier. Every one of those missions was made possible by the extra range the Tokyo tanks provided. Without them, the bombers either couldn't have reached the targets with any meaningful bomb load, or they would have arrived with fuel margins so thin that any combat damage or navigation error would have meant ditching in the North Sea or crash landing in occupied territory. The crews didn't think about engineering innovations or fuel cell design when they strapped into their aircraft before dawn. They thought about the mission, the target, the German fighters they'd face, the flak that would come up in black clouds over industrial areas. But they understood that their aircraft could reach targets their predecessors couldn't. They knew they had hours of flight time that earlier B-17 seconds lacked. And when they came home on 3 engines with battle damage and the fuel gauges showing vapor, when they landed with maybe 20 gallons remaining, and the engineers calculated that they'd covered their wheels with maybe 5 minutes of flying time to spare, they understood that someone back in Seattle had given them just enough fuel to make it. The Tokyo tank system changed mission planning in ways both obvious and subtle. The obvious changes involved target selection. Intelligence would identify a ball-bearing factory in Schweinfurt or an aircraft manufacturing complex in Regensburg, and instead of marking it as beyond reach, mission planners could schedule it. They could calculate fuel requirements, factor in combat reserves, and determine that yes, with Tokyo tanks, we can hit this target and bring the crews home. The less obvious changes involved flexibility. With extended range, mission planners had options. If weather closed in on the primary target, they could divert to a secondary target that might be further away. If German fighters forced a formation to take a longer route home, avoiding a heavily defended area, they had the fuel to do it. Navigation became both more critical and more forgiving. More critical because on a 6 or 7 hour mission deep into Germany, a navigation error that put you 50 miles off course could mean the difference between landing safely and running out of fuel over the channel. The navigators, working in the nose of the aircraft with their charts and instruments, carried enormous responsibility. But the system was also more forgiving because the extra fuel provided a margin for error. If you had to dogleg around unexpectedly heavy flak, if headwinds were stronger than forecast, if you had to fly lower because of weather and that increased fuel consumption, the Tokyo tanks gave you cushion that earlier B-17 seconds simply didn't have. The engineering team, back in Seattle, continued refining the design through 1943 and into 1944. When the B-17G entered production in September 1943, incorporating the chin turret and other improvements, the Tokyo tanks were standard from the first aircraft. All 3 manufacturers, Boeing, Douglas, and Lockheed Vega, built every B-17G with the extended range fuel system. It was no longer an upgrade or an addition. It was fundamental to what the aircraft was. By the time the last B-17 rolled off the production line in July 1945, over 8,000 B-17Gs had been built, every single one equipped with Tokyo tanks. The additional fuel capacity could be increased even further with auxiliary tanks in the bomb bay. These were releasable tanks, essentially large fuel drums fitted with plumbing and mounting brackets that could carry another 820 gallons. 2 tanks, each holding 410 gallons, could be installed in the bomb bay for ferry flights or special missions. Obviously, fuel in the bomb bay meant no bombs in the bomb bay, so these auxiliary tanks weren't used for combat missions. But they extended the B-17's ferry range dramatically, allowing aircraft to be flown across the Atlantic from American factories to bases in England, or from England to bases in North Africa or Italy, without requiring stops in Iceland or the Azores. The combination of Tokyo tanks and bomb bay auxiliaries gave a B-17 a maximum fuel capacity of 3,600 gallons, which translated to a ferry range of over 4,000 miles with no payload. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. But combat operations used the Tokyo tanks without the bomb bay auxiliaries. You needed the bomb bay for what you came to carry. 5,000 pounds of high explosive or incendiary bombs on a typical mission, up to 8,000 pounds for shorter range targets with modified shackles. The Tokyo tanks alone provided the range extension that mattered for the strategic bombing campaign. 400 miles of additional combat radius changed the map of Europe from the American perspective. It made Germany defensible only if the Luftwaffe could maintain air superiority everywhere at once, which by late 1943 they couldn't. German fighter strength was being ground down through attrition. Every mission cost the Luftwaffe pilots and aircraft, and the production capacity to replace them was being degraded by the very bombing campaign the extended range made possible. The fuel system created new challenges for maintenance crews. The Tokyo tank cells were removable in theory, but in practice removing them required taking apart sections of the wing. It wasn't routine maintenance. Once installed, the cells stayed installed, unless there was major battle damage requiring wing repairs. The cells were manufactured from rubberized fabric, layers of material bonded together with sealants that would automatically close small punctures. The technology was similar to what tire manufacturers had been developing for self-sealing automotive tires, adapted for aviation use. When a bullet or shell fragment punctured a cell, the rubber compound around the hole would swell and seal, ideally before too much fuel was lost. The system worked, most of the time. But it wasn't foolproof. Ground crews learned to inspect the Tokyo tank cells during pre-flight checks, looking for signs of leakage or damage. This required opening access panels in the wing, sometimes crawling into spaces barely large enough for a man, using flashlights to examine cells that might have taken damage on the previous mission. Leaking cells had to be patched or replaced, a job that could take hours and required specialized materials. Aviation gasoline was precious, rationed carefully, and every gallon that leaked out of a damaged cell was a gallon that couldn't be used for the mission. More critically, fuel leaks presented fire hazards. One spark, one piece of hot metal from battle damage, and a leaking fuel cell could turn a wing into an inferno. The crews who flew with Tokyo tanks developed procedures through experience, lessons learned sometimes at terrible cost. They learned to activate the Tokyo tank valves at specific points in the mission, usually after takeoff once they'd climbed to altitude and were headed across the channel. The fuel would drain by gravity into the main feeder tanks, which in turn fed the engines. Pilots monitored their main tank gauges, which would show fuel levels staying relatively high even though the engines were consuming fuel, because the Tokyo tanks were constantly replenishing the main tanks. When the Tokyo tanks finally emptied, the main tank gauges would start to drop normally. That change in fuel consumption rate was the only indication that the extended range tanks had run dry. The lack of direct monitoring for the Tokyo tanks bothered some pilots. They were flying into combat with 1,080 gallons of fuel they couldn't see, couldn't measure, couldn't verify, was actually there until it started flowing. What if the cells hadn't been filled properly? What if there was a leak somewhere in the system? What if the valves didn't open correctly? These weren't hypothetical concerns. There were incidents where Tokyo tanks failed to feed properly, where valves stuck, where cells had been damaged on the previous mission and hadn't been adequately repaired. Crews that expected to have hours of additional fuel found themselves running on empty much sooner than planned, forced to leave formation and try to make it home or look for somewhere to land. But those failures were the exception, not the rule. The Tokyo tank system worked reliably enough that by mid-1944, crews simply expected their B-17 seconds to have the extra range. It became part of the aircraft's capability, as fundamental as the defensive armament or the Norden bombsight. The engineering team in Seattle had created a system that integrated so thoroughly into the B-17's operation that it became invisible, which is perhaps the highest compliment you can pay to any engineering solution. When it works so well that people stop thinking about it, when it just becomes part of how things are done, that's successful design. The strategic impact of the Tokyo tanks extended beyond individual missions or even the cumulative effect of those missions. The extended range changed German defensive strategy. Before Tokyo tanks were widespread, the Luftwaffe could concentrate their fighter forces in a relatively narrow band of airspace, the zone where Allied bombers would be operating without escort. They knew roughly where the bombers could reach, and they positioned their defenses accordingly. After Tokyo tanks became standard, that defensive band had to widen dramatically. Bombers could hit targets 400 miles further into Germany, which meant the Luftwaffe had to defend a much larger area. They had to spread their forces thinner, maintain readiness at more airfields, protect more industrial targets. Resources that might have been concentrated against the bomber streams had to be dispersed. This defensive dispersal had cascading effects. German early warning radar networks had to extend further east. Flak batteries had to be positioned around more targets. Fighter units that had been based in France and the Low Countries, where they could easily intercept bombers heading into Western Germany, now had to relocate to bases further inland to protect central and southern German targets. And every resource allocated to defense of the homeland was a resource that couldn't be used on the Eastern Front or in the Mediterranean or in occupied territories. The strategic bombing campaign's goal was to degrade German war production, but an equally important objective was to force Germany to divert resources from offensive operations to defensive ones. The Tokyo tanks contributed to that objective by expanding the zone of threat. By 1944, when the P-51 Mustang arrived in England in large numbers and could provide fighter escort all the way to Berlin and back, the combination of extended-range bombers and extended-range fighters fundamentally changed the air war over Europe. Missions that had been desperately risky in 1943 became routine, or as routine as flying into combat ever becomes. The daylight bombing campaign that had nearly been abandoned after the catastrophic losses of Black Thursday and similar missions became sustainable. Loss rates dropped from unsustainable 20 to 25% down to 3 to 5% on most missions, still terrible by peacetime standards, but acceptable in the calculus of industrial warfare. The Tokyo tanks didn't win the air war by themselves. No single innovation ever does. War is a system of systems, where multiple factors interact in complex ways. But the tanks were a critical component. They gave bombers the range to reach targets throughout Germany. They provided the fuel reserves that meant mechanical problems or battle damage didn't automatically mean the crew was lost. They enabled the strategic bombing campaign to proceed as planned, rather than being restricted to targets within a few hundred miles of English bases. And they demonstrated that sometimes the most important innovations aren't the ones that make headlines or earn medals, but the ones that quietly expand what's possible. The engineering team that developed the Tokyo tanks never received public recognition during the war. Their work was classified, military secrets that couldn't be discussed openly. Even after the war ended and B-17 seconds returned home or were surplused or scrapped, the technical details of the fuel system remained obscure outside aviation, engineering circles. The pilots who flew B-17 seconds with Tokyo tanks understood they had extra range, but most didn't know the specifics of how that range was achieved. They knew they could fly deeper into Germany and make it home, and that was enough. The mechanics who maintained the aircraft understood the system in practical terms, how to inspect the cells, how to patch leaks, how to operate the valves. But the engineering theory behind it, the calculations and design decisions that made it work, that remained in Boeing's technical archives. The historical record is peculiar in what it preserves and what it loses. We know the names of bomber pilots who became aces, even though aces were rare in heavy bombers. We know the names of aircraft designers like Boeing's Ed Wells and Gifford Emery, who designed the B-17's basic airframe. We know the commanders who planned missions and the generals who directed the strategic bombing campaign. But the engineers who developed the Tokyo tanks, who solved the specific technical problem of adding 1,080 gallons of fuel capacity to an existing aircraft design without requiring major structural modifications, their names didn't make it into the official histories. Their contribution was recorded in technical manuals and engineering reports, documents that described what was done but rarely credited who did it. This anonymity was typical of wartime industrial production. Thousands of engineers worked on thousands of problems, most of them working in teams where individual contribution was difficult to isolate. The culture of engineering emphasizes collective problem-solving over individual achievement. When a team develops a solution, the solution gets attributed to the company or the project, not to specific people. And in wartime, when everything was classified and secrecy was paramount, the emphasis on collective anonymity was even stronger. Nobody wanted individual engineers identified because that information might be valuable to enemy intelligence. What mattered was the result, the capability delivered to the forces in combat, not who specifically deserved credit. But the result was remarkable. Between the time Tokyo tanks entered service in April 1943 and the end of the war in Europe in May 1945, 8th Air Force flew tens of thousands of bomber sorties deep into German territory. The exact number of sorties that were only possible because of extended-range fuel tanks is impossible to calculate precisely, but estimates suggest over 15,000 B-17 missions relied on Tokyo tanks to reach their targets and return. Each of those missions carried a crew of 10 men. Each mission struck industrial targets that degraded Germany's ability to wage war. Each mission that ended with the aircraft landing safely back in England was a mission where the fuel system worked as designed, where the extra range meant the difference between success and loss. The human cost of the air war over Europe was staggering. The 8th Air Force alone lost over 4,000 heavy bombers and 26,000 aircrew killed in combat. Tens of thousands more were wounded or became prisoners of war. For every aircraft that made it home, someone else's didn't. For every crew that survived their tour of 25 missions and rotated back to the States, others died over Germany or France or the North Sea. The Tokyo tanks couldn't prevent those losses. No fuel system could protect against a direct hit from flak or a 20mm cannon shell through the cockpit. But the tanks could and did reduce losses from fuel exhaustion, from aircraft that couldn't make it home because they didn't have enough range. They provided the margin that meant engine damage or navigation errors were survivable rather than fatal. Maintenance records from 8th Air Force bases show a measurable decrease in fuel-related incidents after Tokyo tanks became standard equipment. Fewer aircraft ditching short of base. Fewer emergency landings at forward fields because the crew couldn't make it back to their home station. Fewer missions aborted because fuel calculations showed the aircraft couldn't reach the target and return safely. The improvement wasn't dramatic in any single instance, but accumulated across thousands of missions. It was significant. Crews that would have been lost came home. Aircraft that would have been written off landed safely and flew again. The incremental gains added up. By late 1944, the strategic bombing campaign had achieved most of its objectives. German oil production was devastated, fuel shortages crippling the Luftwaffe and Wehrmacht. Transportation networks were shattered, making it difficult to move troops or supplies. Industrial production was dropping as factories were destroyed or damaged. Germany was still fighting, and would continue fighting until the bitter end in May 1945, but the capacity to sustain that fight was being systematically destroyed. The bombers did that. The B-17 seconds and B-24 seconds that flew day after day into German airspace, dropping their loads on military and industrial targets, breaking the machine that powered Nazi aggression. And they could only do that because they had the range to reach the targets that mattered. The post-war analysis of strategic bombing remains controversial. Some historians argue the campaign was decisive, that it destroyed Germany's ability to wage effective war and hastened the Allied victory. Others contend that the resources devoted to strategic bombing would have been better used supporting ground forces, that the campaign's results didn't justify its costs. The debate will likely never be fully resolved because it's impossible to know what would have happened if different choices had been made. But what isn't controversial is that the campaign happened, that it required bombers capable of reaching targets throughout Germany and occupied Europe, and that the B-17's extended range capability was essential to making that possible. The Tokyo tanks were retrofitted to some earlier B-17F aircraft through modification centers, though this was less common than simply replacing older aircraft with newer ones that had the tanks built in from the factory. The modification process was complex and time-consuming. It required partially disassembling the wing, installing the rubberized cells, routing new fuel lines, installing control valves, and then reassembling everything and testing it thoroughly before the aircraft could return to combat operations. For aircraft that were already war-weary, showing the cumulative effects of dozens of combat missions, it often made more sense to retire them to training duties or non-combat roles and replace them with fresh aircraft from the production lines. The newer aircraft came with Tokyo tanks, along with other improvements and modifications, and they hadn't been shot at yet, which meant they started service without battle damage or structural fatigue. The Navy version of the B-17, designated PB-1W, used for long-range patrol and airborne early warning after the war, featured even more fuel capacity. Navy aircraft modification centers installed 300-gallon drop tanks under each wing in addition to the Tokyo tanks in the wings, bringing total fuel capacity to 3,400 gallons. This gave the PB-1W an endurance of over 22 hours, allowing it to patrol vast expanses of ocean looking for Soviet submarines during the early Cold War. The fact that the B-17 airframe could accommodate such extensive fuel capacity modifications speaks to the basic soundness of the design. The aircraft structure was strong enough to handle the additional weight. The wing design could incorporate the extra tanks without compromising flight characteristics. The modifications were possible because the original design had been done right. In the decades after the war, as aviation technology advanced and jet aircraft replaced propeller-driven bombers, the B-17 passed into history. Most were scrapped, the aluminum recycled. A few were preserved in museums. Static displays showing visitors what the bombers of World War II looked like. A handful were restored to flying condition by dedicated aviation enthusiasts, kept airworthy as living history, demonstration aircraft that appear at air shows and allow people to see and hear what a formation of B-17 seconds sounded like when they passed overhead. These restored aircraft, the ones that still fly today, are mostly B-17Gs, the final production version, which means they all have Tokyo tanks. The extended-range fuel system that was designed in Seattle in 1942 is still there, still functional, still part of what makes these aircraft capable of long-range flights to air shows across the country. The legacy of the Tokyo tanks extends beyond the specific aircraft and the specific war. The principle they embodied, finding unused space within an existing structure and repurposing it for additional fuel storage, influenced post-war aircraft design. The idea of flexible fuel cells that could be fitted into odd-shaped spaces became standard practice. Modern aircraft, both military and civilian, use flexible fuel bladders in their wings and fuselages, descendants of the rubberized cells the Boeing engineers developed for the B-17. The concept of self-sealing fuel tanks, which the Tokyo tanks incorporated, became mandatory for military aircraft and was adapted for civilian use in situations where fire safety was critical. The engineering solutions developed under the pressure of wartime necessity became the foundation for peacetime improvements. The B-17's operational history demonstrates how incremental improvements compound over time. The original Model 299 prototype that flew in 1935 bore only superficial resemblance to the B-17G that rolled off production lines in 1944 and 45. Every aspect of the aircraft had been refined, modified, improved. More powerful engines, better defensive armament, refined aerodynamics, improved systems. And among all those improvements, the Tokyo tanks represented one of the most consequential because they addressed one of the most fundamental limitations: range. You could make a bomber faster or tougher or more heavily armed, but if it couldn't reach the target, none of those improvements mattered. The Tokyo tanks ensured the B-17 could reach the targets that needed to be hit. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.